So section 4.3 brings us into Newton's second and third laws. Okay, Newton's second and third laws. We're going to talk about mass, force, and acceleration, how they're related. And then we're going to talk about what are called action-reaction pairs. Now to start this, we're going to take a look at this. This is how this works. I don't know, to be honest. Depends on if there's left it over or not. So, if it's locked, the key should be hanging up. So we're going to do this lab beginning of next week. And what we're going to do, actually, is determine what's called the coefficient of kinetic and static friction between surfaces. To do that, what we're going to do next week is we're going to hook up this little scale. It's a dual range force sensor. It measures how much force is applying. So if I, ever hear, a boxer punches with so much pressure, how much pounds per square inch, it has to do with the force they're applying over the amount of area of their fist. So with this measures the amount of force you're applying. I can hook it up to, your calculator and pull on it, and inside your calculator, and it'll measure it here with what's called a spring scale. Okay, it'll measure the amount of force, and you can also measure the acceleration of the object, and you can, plot those two things together. So we're going to do that next week in the lab. Let's say we did it, and those are the results. And we're going to do it with these three surfaces next week. You're going to have different cork. This is felt, and this is Teflon. So we're going to come up with three different coefficients of friction for those materials. So let's say here, though, we did the lab already, and we're trying to figure out that there's a relationship for sure. There's a relationship that relates acceleration and net force. What would the factor be in these four cases? When the acceleration is 2, the force is 6. When the acceleration is 5 meters per second squared, the force is 15 newtons. When the acceleration is 7, what do you got, Sarah?
It's like a factor of 3.
Yeah, it's a factor of increase of 3. How do you get from this to this? You multiply by 3, right? Each of these are multiplied by 3. Multiply by 3 for all of them. So this is like times 3, and you get to the next answer there. So that's the factor of increase. Well, the question that you might want to pose is, what is that factor? What is 3? 3 is not just some number. It's got to be some material property of something that's going on. So we're going to figure that out. We're going to recognize that if we take acceleration, right, jot this down, acceleration, and multiply it by some factor, 3, we get force. That's what's happening here. We're taking our acceleration column, we're multiplying that by 3, and it's giving us the force column. But the problem is, what is 3? And some of you might have an idea as to what 3 is, okay, because maybe you remember from physical science what variable goes in that place, F equals, and you fill in the blank. Or maybe because you're just looking and understanding the physical nature of the problem. But let's say nobody in the room knew what it was. Okay, make believe nobody knew what 3 was. How could we possibly go about figuring it out? There's a way we can do it. There's a way we can figure out what 3 is. And it's mathematical in nature. How can we figure out what it is?
Is this like assuming that you know acceleration?
Sure.
Oh, then you just divide it.
No, but I mean, what is it physically? What is it? Not what is the number. The number is 3. I'm saying like 3 what? Is it 3 meters? Is it 3 seconds? What is it a measurement of? What is 3 a measurement of is the question. How could we figure out what 3 is a measurement of using some sort of mathematical approach, not just knowing it from physical science?
Well, you know that it can't be velocity because there's acceleration in each one, and therefore the velocity will be constant.
Okay, you know it can't be velocity. There's another reason, actually, not because of what you said, but it definitely can't be velocity. That's for sure. It's not because of that, because think about it. Well, you would have to be VF or VI. You can't have like just V there, pretty much. It would have to be like delta V or something. But it can't be velocity for sure. There's another reason it can't be velocity. How can we determine what it is? What does A represent again?
Acceleration. So
How do I know that when I'm taking a test and it says an object is moving and it doesn't say with an acceleration? Let's just say an object moves at with 3 meters per second squared. What tells you that it's acceleration? Yeah, the units, don't they? Don't the units tell you about something? So what do you think we should do? Absolutely. Units of acceleration are... We don't know the units of this. Leave them blank. What is force? Newtons. But what is a newton? Look at 4.1 if you have to. In section 4.1, I outlined to you what a newton is made up of. what the components of a Newton are. Katie.
Kilogram minus meter over seconds.
Yeah, and that hyphen is a times, actually. Yeah, I know it's a little misleading. In your textbook, and that's why I did that. In your text and a lot of old texts, when you're looking at units only, a hyphen actually means times. You can never have minus with units. It's not possible. Units cannot have a minus in them ever. So whenever you see a hyphen, it actually means times, which is misleading. Anyway, back to the question at hand. Take a look. What's missing? What's the balance? The balance the sides. Kilograms. This has got to be kilograms. Look at it and it makes sense, please. Kilogram meter per second squared. Over here, we only have meter per second squared. So as a result, if we're missing something here, and this is what's extra, that must be it. So the value of 3 is a measurement of the object's mass. I knew you wanted to say that earlier. Very good. Okay, it's a measurement of the object's mass. So this is really m times a. And this gives us Newton's second law. F equals ma. Easily derivable from an experiment. And that's what I was trying to show you. This was the way you take an experiment and you derive what something is. Let's go. So Newton's second law tells us the following. And it's the exact same thing we wrote down. We just rearranged the formula. But the second law tells us specifically that an object's acceleration is proportional to the net force. Well, make sense of that. Think about the last slide. If I push harder on Natalie's pencil bag, I push lightly, not much acceleration. Push a little harder, a little more. Push even harder, it accelerated more to get up to a higher velocity, and then it slowed down. So the first part of this definition says an object's acceleration is directly proportional to the net external force. So the overall force is proportional to the acceleration. That makes sense. Push harder, it goes faster. That's why they're in the numerator, A and F. But what about the mass? How is that related to acceleration? If it's in the denominator. We did this in the beginning of the year with density. Remember that?
If it's indirectly related, so if it goes up or down, it's going to change.
Yeah, it's going to be the opposite. So, ready? If I have this object, and then I have, I'm sorry, I'm using your stuff. So I have this bag, this object. I push this object, it moves. Same force. I'm literally applying the same force. Did it move as far? Why not? Because there's more. There's more mass there. And we talked about last class how we can think of that as more inertia, but it's also because there's more mass. You increase the mass, it decreases the acceleration. It's logical. It's harder to move something that's heavier. It's got more mass. So acceleration and mass are indirectly related or inversely proportional. If you want to put indirectly related in place of that, you can. Inversely proportional and indirectly related are the same thing. Now, how is this the same thing as the last slide? Just multiply both sides by m. Multiply by m. Multiply by m. M cancels, giving me F equals ma. Newton's second and probably most famous law of all time. From this, you can derive momentum. From this, there's so much more you can do. Okay, F equals ma, one of the most fundamental governing laws of motion. Now, this is the global vector F, meaning some force in any direction. But I could also look in the x direction only. And I could look in the y direction only. So what we're going to write from this is the following. We're going to write two equations. The first one will say F net in the x direction equals mass times acceleration in the x direction. And then in the y direction, it's going to be the same thing. F net in the y direction equals m times a in the y direction. Okay, again, F net. What does net mean again from last class? Net, total, or overall force. The overall force in the x direction equals mass times acceleration in the x direction. See how we're going to break it into components again, like we did in the last chapter. The overall force in the y direction equals the mass times the acceleration in the y direction. Okay, yeah, I can make this course really easy and dumb it down a lot and only look in one direction. But that never happens. You're never going to have an instance in real life where it's in one direction at all. So I'm trying to give you an idea of an approach where, bless you, imagine a force is applied at an angle. We're going to see how we're going to break that into components of x and y in this section. Let's see. Let's look at the first example. Okay, we'll probably finish off the... Sierra, why don't you read it for us, please?
Example 1. A space shuttle astronauts experience accelerations of about 35 meters per second squared, almost 4 grams during takeoff. What force does 35 kg astronaut experience during this acceleration?
Okay, so almost 4 Gs, actually, that's what that is. I should have put an apostrophe. 4 Gs means almost 4 times Earth's gravity. Okay, you feel literally 4 times as heavy as you feel right now. You think when you're walking home, you feel like you're tired? Imagine multiplying your weight by 4. That's what astronauts feel when they're in space sometimes, especially on takeoff and when they have to do some sort of acceleration. So what force does a 75 kilogram astronaut feel if this is the acceleration? So this is a very easy example. Let's list what we know. The acceleration is 35 meters per second squared. The mass of the astronaut is 75 kilograms. And this is the only time that we don't have to worry about making kilo back to grams. Kilograms are actually your base unit of mass. Not, I shouldn't say base, but they're your fundamental unit of mass. You're not going to use grams for mass. You're going to use kilograms always. You don't have to convert to grams. You always leave it in kilograms. Because the Newton was derived as kilogram meter per second squared. That's why that's true. So Newton's second law tells us the following. It is. It's annoying because you think like, I want everything to be in base units except for mass. Mass is always in kilograms.
And is there ever like
So if you
equations that go between this and something that the base equation needs to be in grams?
No, unless you like do something where you're looking at like maybe some nanotechnology in the field of physics where you're going to work on a microscopic level and you're working with some chemistry people. A lot of the time they use things in grams. So then, sure. But the basic laws of macroscopic physics, like everyday physics, uses kilogram as the unit of mass.
That's just because we use kilograms and that's why.
Yes, but it's also because it makes more sense. If you measure your mass and you're from how many people's families from Europe here? Do your parents ever talk about their mass in kilos? Do they talk about kilos ever? Do you know your mass in kilos any chance? A kilo is 2.2 pounds. So just divide your current weight by 2.2, you get your mass in kilos. So if you're in Europe, somebody might say, I'm only 70 kilos. 70 kilos would be like 160 pounds. So 70 kilos is more reasonable than saying 7,000, right? 70,000 grams. So kilograms are more reasonable for everyday life than grams are. A gram is like a paper clip. If you start measuring mass of everyday objects in grams, the numbers are going to be so great that kilogram was used more widely, so Newton used kilogram for Newton. Yes, capital calorie is actually a kilocalorie. It means 1,000 calories. Our actual calorie is like a very small unit of energy measurement. You learned that in chemistry. We're going to see it this year also.
so like, if you were to give us a problem on the test that was like,
You leave it in kilograms.
no, but if you gave it to us in grams.
You convert to kilograms. Okay, again, everything's in kilograms for this chapter. So if I told you it was 500 grams, that's a half a kilogram. You have to write 0.5 kilogram. What do you get? What do you get? What do you get? What do you get? This is the easiest problem you could ever imagine, right? Multiplying two numbers.
3,625.
Units? Newtons. How do I know it's newtons? 2 reasons. 1, it's force. Force is measured in newtons. 2, kilogram times meter per second squared is indeed a newton. That's what a newton is made up of. Okay, that's what a newton is made up of. I'm going to hold off there. Okay? In this second example here, we have a bowling ball that's at rest initially and it's dropped from the top of an 11-meter building. It hits the ground a second and a half later. Find the mass of the ball if the net external force on the ball is negative 74 newtons. Okay, find the mass of the ball if the net external force is negative 74 newtons. What would you do for a problem like this? How would you approach it? What might you do to start all these kinds of problems? What do you do to start all the problems? Even in chapter 3 and 2, what do we always write down first?
Givens?
The givens, yeah. The givens. So let's start by listing our givens. So the height of the building is 11 meters. So we know already that y will be negative 11 meters because it's going to fall down 11 meters. We know that the net force acting right? Find the mass of the ball, the net external force. The net force acting is negative 74 newtons. Now, before I go further, which way is that force acting? Does negative mean left or does it mean down?
Down.
Why?
Because it says it's dropped from the top of the building.
Yeah, so you know A, it's falling down, and B, what could cause something to drop? It's weight or gravity. So this is a force acting down, not to the left. It's the y direction. Okay, the negative 74. We're then told that it takes 1.5 seconds to hit the ground. So that's how much time has elapsed. We know Earth's gravitational acceleration is negative 9.81. God bless you. Meters per second squared. So in this part, we're going to take a look. We're going to say to ourselves, what information is extraneous? What don't we need here? Because not every problem gives you the exact perfect information. Sometimes you get a little extra piece, right? Just to give you more context of the problem, but you might not use that mathematically.
You don't need to know why or something.
You don't need this or this. Okay, why don't we need those two values? What reason don't we need those two values then, Sarah?
It's not in our formula.
Yeah, the formula we're going to use for net external force is net external force equals NA. So as a result, we don't need to think about y or t. I mean, y and t could help us, right? What could y and t give us? It could give us maybe the initial velocity. Well, that's 0 because it's dropped. It could give us the acceleration if we solve, but we already have that. So that information is extra. We don't really need it. And if you didn't recognize that, here's how you can think about it. It says find the mass. We've only had one formula this year, right? So far that involves mass. That's it. And that formula is F equals M times A. All right, that's the only formula we've had all year with mass. So it's the only formula we can use. And clearly we know that F is F net, really. Net force equals Ma. And A is the acceleration of gravity. So let's go ahead and figure out what the mass is. We go ahead and divide by A on both sides, giving us negative 74 newtons over negative 9.81 meters per second squared. That yields a mass value of 7.5 kilograms. Okay, remembering that our base unit in this class for mass, or our fundamental unit, I should say, not base, or fundamental unit here we're going to use is kilograms. Okay, because a newton is a kilogram meter per second squared. So let's write down a little star here and a little note, please. These are the notes that always help, right? Let's write down a little star. Maybe you could jot this down. I'm gonna dictate. So if you ever want to find out the mass of an object, right? Ever want to find out the mass of an object? You could take the force felt on the object. You can take the force felt on the object under free fall, which is known as its weight, right? Take the force felt on an object under free fall. In parentheses, it's like its weight, aka Fg. Remember Fg from the free body diagram we were drawing? Aka its weight, and divide by negative 9.81, or gravity. Okay, so take the weight of the object, in this case it's 74 newtons, divided by 9.81, they're both negative because they both act down. Okay, take those two numbers, divide them, giving you the mass of the object. This will always give you the mass of any object on Earth. So if you know the weight of this notebook, and you know that it weighs, let's say it weighs 1 kilo is 2.2 pounds, this is like a quarter of a pound, an eighth of a kilo. So, sorry, the mass is about 8.125 kilograms. We can find out the weight by, instead of dividing, we can simply multiply. We're going to see that in section 4.4 when we go into those formulas. Let's look at a third example just so we can incorporate kinematics. That's where an object's motion is changing. It has acceleration, it has a change in velocity. It's got a few different things involved. So we're going to go ahead and figure out what the force would actually be on this object to accelerate. So it goes from 6 meters per second to 15 meters per second. Right then you think change in velocity, right? Change in velocity. You should think of acceleration right away. It happens in 10 seconds, which allows you to calculate the acceleration. And you're given the mass of the object itself. So this, right here, okay, is your delta V, which is, remember, final minus initial. You can do it that way. You could say that this is going to be 15 minus 6, or 9 meters per second. You know that the time it takes to do this is 10 seconds. You could use this formula right here. Okay, that's one of the formulas we learned at the beginning of the year. Or you could use VF equals VI plus AT. Okay, you could also have done this. I'll put this on the side. Okay, you could have done this, list all three separately, and utilize this formula as well. Plug in for VF, plug in for VI, you're still going to have 15 and 6. You're going to subtract the 6 to give you 9. You're going to divide by time. Okay, it's the same thing we'll do here. We'll take a 9 and divide by time. You're still going to get the same answer either way you do this problem. The key here is to recognize that you have a change in velocity. As soon as you have a change in velocity, you should think acceleration always. Here's acceleration here, or getting acceleration here. Why isn't acceleration negative 9.81? Why isn't the acceleration on this object negative 9.81? Why are we actually determining an acceleration?
It says like the object accelerates from the velocity, so we know it's not.
Yeah, it's not falling. It's not a free fall. Okay, very good. If it said it's accelerating by falling downward, or it's accelerating as it falls to the earth, then you could assume acceleration is negative 9.81. But this is an object that's constantly moving horizontally. We don't really know which way it's moving. It could be moving horizontally, it could be moving at an angle, none of that's given. But that's not necessary to solve. What's necessary to find the external force on an object is acceleration and mass. Okay, acceleration is something from chapters 2 and 3 that we kind of know already. We kind of remember acceleration. So let's go ahead and figure out what that is. We have our formula here we'll just utilize. We'll plug in 9 as our change in velocity, and 10 as our time period. Okay, anything divided by 10, just move the decimal, please. You don't have to actually use your calculator. 0.9 meters per second squared. Are we done with the problem? Whenever I prompt that, it's usually no, right? What else do we have to do still? What else do we still have to do here? How do I find that overall force acting on this object? How do I find the overall force? I know the acceleration, right? What else do I need besides acceleration to find force? What else do I need besides acceleration in order to find the force on the object here? Just take a look at your formula. What's the missing variable that we don't have? Emma? The mass. The mass is necessary. So we need to know what the mass is multiplied by the acceleration. Well, the mass happens to be given as 25 kilograms. Okay, that was given in the problem. It says if the object's mass is 25 kilograms, what net external force must be applied to accelerate this object? So as a result, we could take 25 for our mass. And again, that's in kilograms, not in grams. If your mass was given in grams, like say 1,000 grams or 1,500 grams, you have to convert. Times the acceleration of 0.9 meters per second squared. We know that the units are newtons because it's a force, and kilogram times meter per second squared is a newton. 22.5 newtons. Okay, 22.5 newtons. Now, I want you to have some context. So if somebody go to Google real quick, and just type in 25 space N and 25 newtons to pounds. 25 newtons to pounds. Type in 25 N space, the word 2, T-O, space, and then LB for pound. What is it then in pounds? 5.62 pounds of force. So think about that logically. If you've lifted weights before, a 5-pound dumbbell is usually one of your lighter dumbbells, right? It's like a small dumbbell that like sometimes you use for aerobics and stuff, or people are doing like shoulder workouts because your shoulders are weaker muscles than the rest of your body. They're the light ones. So that amount of weight to lift is not very much, right? So relatively speaking, this is not a very large force that needs to be applied. to get it accelerating. Why? Well, look at the acceleration. It's a very small acceleration. It's not a large acceleration. Think about an object falling. That acceleration is negative 9.81. I'm accelerating, or we're accelerating this at almost a tenth of that rate. So this is not that fast as it is. Imagine an acceleration that's only a tenth of that. That's why you don't need much force. Force of 5 pounds might be like that. Okay, it's not a very large force. It's very light. So you should have context of your answers when you're doing them. Okay, so when you're doing problems on homework, maybe sometimes convert the mass. If you get a mass as an answer, you think about what that means in pounds. Is that reasonable? Like if you get the mass of a box and you end up getting like 0.001 kilograms, it doesn't make much sense. I mean, unless that box is like a jewelry box, or like a, like you put like a ring or any jewelry in, like maybe that would be even that would be probably like 0.01 kilograms. But if you get something unreasonable, understand why the answer should or should not be accepted or maybe rechecked. Okay. Third law, and this is the law that almost everybody seems to always memorize for sure. We need to make sure we understand it as well. Okay, so for every action, there's an equal and opposite reaction. The other day, I think, Frank, were you and I demoing with the arms? Yeah. So one person applies a force. If the other applies the same force, there's a balance, right? There's equilibrium. Well, those are two different external forces applied to one another, as opposed to me doing this, right? If I push on this podium, if I push hard enough, I mean, if anybody pushed hard enough, you could probably like snap some of the fixtures out of the ground, actually. But let's say hypothetically, I'm like pushing with my thumb, right? I'm applying a force. Well, because it's not moving, what must it be doing also?
Pushing back.
It must be pushing back. If it weren't pushing back, it wouldn't be equilibrium. It wouldn't be stationary the way it is. If I hit the wall, when I hit the wall hits back. Okay, that's why you ever see people get angry, they punch the wall, and then afterward they're like, oh my gosh, I think I'm broken up or something. Well, if you make it through the wall doesn't push back as much, right? But if you hit the wall and the wall doesn't actually break, it means that the wall pushed back with the same force you hit the wall with. That's why you end up hurting the pain for other reasons as well. But for each action, there's an equal and opposite reaction. Now, I'm not going to demonstrate this because it's really obvious, but if you take two of these force scales, if this is confusing to you, you're welcome to come in and use these. Take two of these force scales. We're going to use them next week when we determine the coefficient of friction in one of our labs. Take two of them, just hook them together. Okay, and two people hold them. One person pull on one end, one hold the other. But don't pull and like move it. Just pull so that it's stationary. If you connect them, one force sensor might read 5 newtons, what would the other read? Yeah, but equal and opposite, so what is it going to read?
Negative.
Yeah, negative. If one reads positive 5, one reads negative. These, they might both actually read positive, actually, because they both might be magnitudes. But the idea, again, is that for every action, there's an equal and opposite reaction. Okay, an equal and opposite reaction. Okay, so let's take a look at an example. So here we have a hammer that's hitting a nail. So why is the force of the hammer on the nail overcoming the force of the wood on the nail? It says force of hammer on nail to the left, and it looks like a bigger vector than the force of the wood on the nail. What's happening in this example here?
I guess if you hit the nail into the wood, then it must be putting off a stronger force than the wood on the nail, because if the wood on the nail was pushing back a harder force, the nail wouldn't actually go into the wood.
Yeah, exactly. It's just like the idea of punching through a wall. A nail is exactly that. You hit the hammer, you hit the nail with the hammer with a certain amount of force. If that force cannot be withstood by the wall cannot respond with as much force. So the wood obviously has some sort of a force on the nail itself. Why? Because of friction for sure. Like think about you hit a nail into wood. As you're hitting that nail in, it actually heats up. If you touch a nail after you like pry it out of wood, or after you actually hit it into wood, the head of the nail will be a little bit hot. Take the back end of a hammer and pry a piece of nail out of a piece of wood. Because of the nail rubbing along the wood, the friction, it'll actually be hot when it comes out. So that's basically what's happening here. The head of the nail can puncture the wood because it's such a small area. We'll talk about pressure in a later chapter in the year. And the pressure is so great that it actually goes through into the wall. So as a result, the wood itself cannot supply the same force back. So this is not an example of an action-reaction pair. Okay, this is not an example of an action-reaction pair because it's not balanced. All right. The last thing we want to talk about quickly is thinking about field forces. Okay, field forces. Remember, what were field forces? We're going to talk about how they're reaction and action pairs. But what were field forces? How are they different from contact forces? All right, this is my contact force. What was a field force?
What's a field force like? It's like magnets or like static electricity with a balloon or something. It's like pulling them away.
That's exactly right. It's something where you have examples like magnetism, static electricity, where an object can be moved or pulled away without actually touching it. That's the thing. So like if I'm some sort of electric source and I'm a positive charge, and there's some sort of electrical charge over there that's negative, opposites attract electrical charges. So they're going to pull toward each other. So if I'm Earth, right, I'm Earth and I can exhibit all this gravity. How many people have seen Family Guy before? Okay, do you remember the episode where Peter keeps getting fatter and fatter and develops his own gravitational pull? And at one point Brian takes the TV, he's like, Peter, you're getting so large, you've developed your own gravitational pull. And Peter's like, what are you talking about, Brian? And Brian starts throwing stuff at him, and what happens? Those objects start to orbit around Peter. The amount of force that he gives off because he's such a large mass is felt by the object when the object pulls back. Why isn't Peter getting pulled by the TV? Because Peter's mass is so great relative to the TV itself. So the Earth, although like what, I'm jumping right now, as I jump and I come back down, the Earth's pulling me down, right? But I'm also pulling the Earth back up with the same force. That's kind of wild to think about. My weight might be like, I don't know news to be honest, what would my weight be? You said earlier that, what was in that? It was 5 pounds. How many newtons was that? 22.5 newtons? Okay, so yeah. Let's say the weight of a person is 900 newtons, relatively speaking. And the person jumps up in the air. Well, the Earth pulls back with 900 newtons. That means you pull on the Earth with 900 newtons. But think about it logically. What can we say? Well, we can say this. This is Newton's second law. So, if my weight is, again, 900 newtons, my weight is 900 newtons, and I'm getting pulled to the Earth with an acceleration of negative 9.81 meters per second squared, I could figure out what my mass is by dividing those two numbers, right? 900 over negative 9.81, and this force should be negative because it's down. So I divide those two, I can come up with a mass. We're going to get something, what is this going to be? Let's see, if it was exactly divided by 9, it'd be 100, right? It'd be 100 is divided by a little more than that, so it's going to be something less than 100. Okay, so the mass will be something less than 100 kilograms. I don't even care what it is right now. But I then go to the reverse. Okay, go to the reverse and think about the Earth now. Well, the Earth feels the exact same force because of Newton's third law. It says for every action there's an equal and opposite reaction. So the force felt by the Earth is still 900 newtons also. We'll say that it's positive because it's being pulled up, right? The Earth is being pulled up toward my body. Okay, so the force felt by the Earth is 900 newtons. Why doesn't the Earth move? Why doesn't the Earth get pulled up to my feet? How come the Earth pulls me to it? Why can't I have enough magnitude or gravitational pull in my body to pull the Earth upward?
Is the Earth's heavier?
Yeah, the Earth's mass is so ridiculously great that, plug in a number here. First of all, what do you think the Earth's mass is? You have any idea at all? I don't really know, to be honest with you. I know it's something with exponential notation involved. I think it's something times 10 to like 23rd or something crazy or something like that, kilograms. So pick a really big number for a second. It doesn't matter what it is. Pick a billion. That's not even a big number relative to the Earth's mass. Let's say it's 1 billion kilograms. Put 1 billion in here, divide it into 900. What's the acceleration going to be? What kind of a number? If you divide 900 by 1 billion, what kind of an acceleration are you going to have?
Crazy decimal.
Yeah, a very, very small value, a crazy small decimal. So the Earth is feeling acceleration every time you jump. And there was like this really, I can't find physics post a long time ago that what would happen if everybody on the same side of the Earth jumped at once? And what if it was all timed out that everyone on the entire hemisphere, right, one half of the sphere of the Earth, jumped at the same time? If everyone on the Earth jumped at the same time, then it would be equilibrium, right? The Earth would kind of be pulled in every direction at once. But what if everybody on like this point of this part of the Earth all jumped? Would the Earth get pulled up? Would it be enough force to pull it up? No, it would not. But the idea posed was really kind of interesting to think about. Because enough mass of enough people jumping causes enough gravitational pull upward, we think maybe it could move the Earth. But humans even sum together don't even come close to the Earth's mass. Okay, just think about physically volume and space and make sense of it. Right? The Earth is maybe, if the Earth were this big, humans are like the size of a piece of sand, if not smaller. So put a bunch of sand around an object this big that's solid, right? Throughout. All those sand particles won't even come close to being the same mass as the actual object in the middle there. Okay, so again, because this number is so large, the acceleration the Earth feels will be so small. Okay? Same force felt by the Earth, but the acceleration on the Earth is so little that the Earth doesn't actually move because of you. Okay? Your pull on the Earth does not cause it to move. This homework over the weekend, that's good. You might not have finished it. So please finish this one up tonight. Okay? Please finish this homework up tonight.